Please open in your learning workbook to page 222. We will now complete the final learning objective from this section. Use exponential and logarithmic equations in applications. The real world is full of situations and problems that can be solved using exponential and logarithmic equations. Here are just a few of them. Continuous growth or decay. There are two equations that are typically used for continuous growth or decay. They are really the same equation, but the variables are slightly different. The first is a equals pe to the rt. Sometimes you will see that as f equals pe to the rt, but they're the same equation. The second is a of t equals a naught e to the kt. The first equation, a equals pe to the rt, is typically used for money, but can be used for anything that grows continuously. The second equation, a of t equals a naught e to the kt, is used for anything that grows or decays continuously. This includes money, but also includes things like radioactive materials, which is an example of decay, population, which is an example of growth, bacteria, which is an example of growth, carbon dating, which is an example of decay, etc. A and a of t both represent the amount at a particular time. P and a naught both represent the starting amount, the amount when the time is 0. That's the reason for the little 0 next to the a. The 0 represents the time is 0, and the a represents the amount. So when you put them together, a subscript 0, sometimes pronounced a naught, represents the amount a when the time t is 0. The mathematical constant, e, is the base of both equations. Remember that e is approximately 2.7. The values of r and k represent rates of growth or decay. And finally, t represents an amount of time. Let's look at an example. The number of bacteria in a certain population increases according to a continuous exponential growth model with a growth rate parameter of 2.5% per hour. How many hours does it take for the size of the sample to double? Note that this is a continuous exponential growth model. Do not round any intermediate computations and round your answer to the nearest hundredth. All right, before we begin solving this problem, there are a few things that you want to take special note of. The first is that it is a continuous model. This is telling us what equation we should use. We should use the equation a equals pe to the rt, or a of t equals a naught e to the kt. Remember, those are the same equation. The second thing we want to pay attention to is the fact that it says growth. With growth, r in this equation, or k, is going to be a positive number. But if it says decay, then r or k is going to be a negative number. The third thing you want to pay attention to is this last sentence. Do not round any intermediate computations. That means don't round in the middle of a problem. Don't convert anything to a decimal until you have your final answer sitting in front of you. All right, here comes the solution. This has a continuous growth model, so we're going to use this formula, a equals pe to the rt. I will sometimes refer to this as the Pert formula. We are asked to find the doubling time. That is, the time it takes for the size of the sample to double. If the initial size is p, then when the doubling time is reached, the size will be 2p. This makes sense if you think about it. If you start with 3, when you double it, you'll have 6. When you start with 10, when you double it, you'll have 20. When you start with 100, when you double it, you'll have 200. So if you start with p, when you double it, you'll have p times 2, which is 2p. Using the equation above, with the growth rate parameter r equals 2.5%, and converting that to a decimal, which is 0.025, we get the following. The a part of our equation will be written as 2p, because we are doubling. P remains as p. E is a mathematical constant. R is the value we found, 0.025, and t remains as t. Notice that both sides of the equation have p, so we divide both sides by p, and they both cancel out. We're now left with 2 equals e to the 2 equals e to the 0.025t. This is an exponential equation of type 2. And if you remember your skills from the previous learning objectives, you know that we will use a logarithm to solve this problem. we have to take the logarithm of both sides. And because we're interested in a decimal answer, we have to take the logarithm using base 10 or base e. Well, it just so happens that the base in this problem is e, so let's use base e and take a natural log. So we take the natural log of both sides. Instead of 2, we now have the natural log of 2. Instead of e to the 0.025t, we now have the natural log of e to the 0.025t. Now, the natural log of e to the 0.025t is equal to 0.025t. That may not be obvious as to why that's true, so let me show the work. We're starting here at the top, natural log of e to the 0.025t. Remember, natural log is the same as log base e, so that's the same as log base e of e to the 0.025t. The argument of my log has an exponent, so I use the property that allows me to move it to the front, so then I have 0.025t times log base e of e. Whenever there's a number for the base and argument of a log, you should ask yourself, can that be rewritten in simpler form? Log is EGOB. So what is the EGOB? What is the exponent goes on base e to make e? E to what power? Well, e to the first power is e. So the missing exponent is 1. So the value of the logarithm is 1. And since anything times 1 is itself, we get 0.025t. So what we started with and what we ended with are the same. That explains how we got from here to here. Okay, so now we're dealing with a linear equation, and if you want to solve for t, you just have to divide both sides by the coefficient 0.025. So we do that, and we get t is exactly equal to the natural log of 2 divided by 0.025. When you put that in your calculator, you get 27.7258 ... and when you round to the nearest hundredth, you get approximately 27.73. This is the doubling time. This is how long it will take this sample of bacteria to double in size.